Hey, everybody. So we did uh, conservation of momentum in one dimension last week. So this week we're going to do conservation of momentum in two dimensions. This is very similar to projectile motion in two dimensions, where we're going to draw our chart of x and y. And instead of determining the vectors in x and y for velocity and analyzing them independently, what we're going to do is we're going to separate them into momentum in the x before, momentum in the y before, and then momentum in the x prime, and the momentum in the y prime. And remember, prime means after the collision. And because we know that momentum is conserved, we know that the initial momentum in the x has to be equal to the prime momentum, or the momentum after the collision in the x, and same with the y direction. Okay, and so this goes back with the collisions. Really, there's two types of collisions we're dealing with. The hit and stick, so when two masses come together and then they stick together and they have the same velocity after the collision. And then glancing collisions, so now we're going to deal with situations where objects come in and then they bounce off. So then they have a different velocity and magnitude and direction. So we're going to use component method to split those vectors into x and y, and vice versa, to find resultant vectors. Okay. We're going to also do Hooke's law this week. It really just pertains to springs. We had that combo question last week where the spring was compressed and you had to use work to find it. We can now use Hooke's law, which is E, so elastic energy is equal to 1/2 kx squared. And there's a whole note that I'll post about that. Pretty much all you do is you substitute that EE, or the elastic energy, into your conservation of energy equation, just like you would EK or EP, and then use that to solve different situations. Okay. So Hooke's law just pertains to the energy held, potential energy held within a spring. Okay. And so we can shoot things at the spring and measure the compression, or shoot things from a spring. So conservation of momentum in two dimensions. So collisions at 90 degrees and collisions at multiple angles, which are a glancing collision. So we're going to start out with a collision at 90 degrees, which just means that an object is going east and south or north, and then they hit kind of like a T-bone crash, right? So if you're going along one road, someone blows a stop sign and you hit. And then we're going to deal with glancing collisions, where you have you're coming at an angle and then you bounce off at an angle. Once again, we need to remember that conservation of momentum is based on that the momentum before, these should have a little vector above them. So momentum before is equal to the momentum after, or P prime. So in two dimensions, we know that the momentum in the x is equal to the momentum in the x after the collision, and vice versa, momentum in the y is equal to the momentum in the y after. So let's just do a sample problem. So a 750 kilogram truck is traveling at 21 meters per second west, and it hits a 680 kilogram car moving at 18 meters per second south. If the two cars become entangled, so this is a big hint, right? So if it's entangled, we know that it's a hit and stick collision, right? So we know that the velocity of the cars after is going to be the same. So the velocity of the car is going to be equal to the velocity of the truck after the crash. So what is the final velocity of the wreckage? Keep in mind, velocity needs both magnitude and direction. So you'll see, this is unfortunate. So you'll see I split it into before and after. Okay. So in this case, the momentum in the x, so here's our little diagram. The car is going this way. Which one's 750? Yeah. So the truck is going this way, the car is going this way, and then together after the collision, they're going to take off, hit and stick at some unknown velocity vector v prime. Okay, so what we're going to do is we're going to calculate the initial momentum in the x, the initial momentum in the y, and then put them together to make a resultant vector, right? This one's somewhat easier because before the collision, the car has no momentum in the x direction, right? So we don't even really care about that. And then vice versa, in the y direction, the truck has no velocity in the y, so therefore it has no momentum in the y. So this is a pretty straightforward, just vector addition Pythagorean theorem problem. Okay, so we calculate the momentum before and the momentum before for the car and the truck. So 750 times 21 gives us 15,750 kilogram meter per second. And then the car is 12,240 kilograms meter per second. Okay, so we know that the momentum before in the x direction is this, and the momentum before in the y direction is this. If we had multiple angles, these signs would change. We'd have to subtract things, make a resultant vector in the x, but we'll get there in the next problem. So in this case, we know, because momentum is conserved in the x direction, that the momentum in the x is equal to the momentum in the x prime. So we can just redraw and make this new triangle where we take this vector and this vector, the x and the y, and we solve for this momentum vector here using Pythagorean theorem with the new mass of mass 1 plus 2, because we know that it's hit and stick. All right, and so we use Pythagorean theorem, find out that it equals 19,946.9 kilogram meters per second, use tan, and find the angle. So once we have this momentum vector and the angle vector, we can work backwards to find that the wreckage is traveling at 13.93 meters per second at 37.85 degrees. So relatively straightforward. Just to summarize, at 90 degrees, all you do is you take your momentum in the x and your momentum in the y, set them equal in the prime after the collision, redraw, and find what you need after the collision. Now this is where things get a little trickier, but not really, okay? We're going to just stick with our exact same steps of vector additions that we use in forces and move on from there. So when we're dealing with collisions not at 90 degrees, in this case, a 4 kilogram bowling ball is moving east at an unknown velocity when it hits a frozen cantaloupe, which in my opinion, and you all know this, is that the cantaloupe is the third worst melon. Number 1, water. Number 2 is honeydew. And 3 is cantaloupe. Feel free to have your own opinions, even though they're wrong. Okay, moving on. So after the collision, the bowling ball moves at 2.8 meters per second at 32 degrees north of east. The cantaloupe moves at 1.5 meters per second at 41 degrees south of east. What is the initial velocity of the bowling ball? Okay, so basically the way that this works is that we're going to be given what happens after the collision here, and we're going to have to work backwards to find out the initial velocity of the bowling ball. But what we do know is that the initial velocity of the cantaloupe is 0, which is going to be really helpful later. So we have a 6.1 kilogram cantaloupe that fires this vector, and this momentum vector consists of the momentum of the cantaloupe prime in the y direction and the momentum of the cantaloupe prime in the x direction. Keep in mind that the momentum of the bowling ball after the collision and the momentum of the cantaloupe after the collision are going to have opposite signs because one is going up and one is going down. The x one won't matter because they're traveling in the same direction, but these two will. Okay, so here's what we're going to do. We know that the momentum of the bowling ball in the x, after we find it, so we're going to split these into their corresponding components, right? So in this case, I did it all in one step. So in the x, cosine 32, which gives us this vector right here, cosine 32 times 2.8, which is the bowling ball after, times 4, which is the mass of the bowling ball. So this is going to end up with our P prime. And then this is going to give us, in the x direction, our P prime as well for the cantaloupe. And we know that because the cantaloupe starts at rest, it has no momentum. So all of that momentum has to be coming from the 4 kilogram bowling ball, which is equal to m times v, or m1 v1. And so we just isolate and say, okay, all of this has to be at 4.1 meters per second in the x direction. What you will find, and this is a good place to start, but what would happen if this was coming in at this angle? What would we have to do? There's going to be a sample question posted, a tutorial that walks you through how to do something coming in at two angles and then bouncing out. But really all you do is you make your chart and then work through it, just splitting it into components like we did on the prime side. Okay. So for homework, 252, 1 and 2, 253, 1 and 4. We're going to have a quiz at the end of this week on collisions, and then we're going to do a conservation of energy test next week. All right. Hope things are going well, and we'll see you next week. I won't see you. I'm just kidding, but digitally. How do I stop this? Oh, gosh. Oh, boy. Stop.